In this video, we're going to look at an example from electric circuits for the solution of a series of linear simultaneous equations. And don't get hung up on the details of this. The theory you'll learn a little later on. But I do want to show you a little bit of the background, even if you don't follow completely. But the main thing is we're going to come up with three equations that we need to solve. So in an electric circuit, it's a very simple circuit like that where we have a battery and a resistor. The battery is our voltage source. We have a resistor, and the current will flow, the electrons will flow around there. And the simple equation V equals IR, the voltage equals current times resistance. So using our consistent units of volts, amps, and ohms, if we have a 5-volt battery and a 220 ohm resistor, we can calculate the current as shown here. Simple linear equation, only one unknown. Now let's look at a little more complex of a circuit. In this case, the current that's flowing out of the battery through that first resistor reaches node 1, and then it splits. So we have current 2 and current 3 that are also unknowns, and so this system gives us three unknowns, and we need three equations to solve it. The equations come from Kirchhoff's laws. The first one says the current law says the current flow into a node has to equal the current flow out of a node. The second one says around any closed loop that the voltage drops have to balance the voltage increase. We'll show how that works in just a moment. So let's look at node 1 first. We have the current 1 coming in, we've got 2 and 3 going out, and so balancing those we come up with this equation that we're going to call equation 1. Now let's look at the voltage around the left loop, and so we follow it in this direction. We have a step up here from the voltage, we have drops from these two resistors, and so they come up with the second equation here that it only involves current 1 and current 2. And notice that if we go around a loop in a constant direction, that when we have a battery, that's a plus value, and when we go across a resistor, those are negative values. Now there's no battery in the right loop, but you notice here, as I'm going around this loop in this direction, this is in the same direction as the flow. This is against the flow, so we end up with a plus sign there. And so our third equation becomes 220 I2 minus 480 I3 is equal to 0. So there's our three simultaneous equations. And again, as long as we're going around a loop, we have to go in the same direction completely around the loop. So this is a negative, and this is a positive because I'm going in the opposite direction. So again, don't have to worry too much about how we got there, but here's the thing. We end up with three equations for the three currents. And so now we can write those in matrix form. Okay. Now, let's solve this in MATLAB. Start out with, we do our coefficient matrix. Again, rows are elements of a row are separated by spaces or commas. Rows themselves are separated by semicolons. The C matrix is a column matrix. And remember, we said the most efficient way to solve the equations is with the backslash operator, A backslash C. And there's our answers. Now these are in amps, so we can convert those by multiplying by 1,000 to milliamps. And there's our solution, 7.9, 5.4, and 2.5. Of course, you'll notice the 5.4 and 2.5 add up to 7.9. That's the simplest one we look at node 1, that the current in is equal to the current out. It also makes sense that more current would flow through that 220 ohm resistor than the 480. So least resistance means greater current flow. Now that was pretty simple setup and solve, but one thing that's nice about doing this is you can look at variations of the problem very easily as opposed to doing everything by hand. So what about that 480 ohm resistor? Let's try changing it to 220, or to make it 1 kilo ohm, 1,000 ohms. So here's the 480 being replaced by a 220. All we have to do in our equations then is change the 480 to the 220 in those two spots. The constant matrix stays exactly the same, and so we do our solution, and what we find is that the overall current is greater because there's less total resistance, and also I2 and I3 are equal to each other because those two paths now have the same resistance. In the second variation, we've put a resistor with a larger value of resistance on there, the 1000 ohms or 1 kilo ohm. And so again, the only two numbers we have to change are where those show up in the coefficient matrix. Constant matrix stays the same, and there's our solution. So first of all, we notice that the overall current has decreased because there is greater resistance, and also that the flow through current 2 is greater than flow of current 3, simply because there's less resistance along the path, more so than there was when it was 220 and 480. So there's one application of using simultaneous equations. In the next one, we'll look at a problem from statics that will also relate to the homework problem this week.